Hi Chem 101 students, and welcome back for week 6, our first week after our very first exam. So we spent the first section of the class before the first exam defining chemistry, talking about measurements, and also beginning to talk about elements and compounds and basically atoms and what makes one type of atom different from another type of atom. Hopefully you remember what that is. It's the number of protons in the atom as indicated on the periodic table here by the atomic number. So a hydrogen atom is hydrogen because it has 1 proton. The helium is a helium atom because it has 2, and so forth. The atomic number here tells you how many protons that type of atom has, and that's what defines what that atom is and its chemical behavior. So we did define elements as well and compounds. So pure substances can be divided into 2 main big groups, elements and compounds. Elements have all the same type of atoms. So for example, here with neon, it has only neon atoms, which are indicated by these silver spheres. Oxygen is a compound, or sorry, oxygen is an element, not a compound, that has, again, only 1 type of atom. You can see that in oxygen, it comes in units where there are 2 oxygen atoms stuck together. We're going to end up calling this a chemical bond between these 2 oxygen atoms. And when they bond in these units of 2 atoms, we call that a molecule. So we'll be talking a little bit more about molecules today as well. Our focus will be on the naming of compounds. So compounds are going to come in 2 big groupings. One is molecular or covalent compounds. The other is ionic compounds. And we're going to see that some atoms, when they bond to one another, they tend to make molecules and they make what are known as covalent bonds. Other atoms, when they bond together, they make ionic bonds, and we'll talk about what these 2 types of bonds are. So you can see the difference here with the water. So water is a molecular type of compound that is made from covalent bonds between atoms, and we can see that they come in individual distinct units. Here's 1 water molecule, here's another, and here's another, and each of these units has 1 oxygen atom indicated by the red sphere and 2 hydrogen atoms indicated by the white sphere. Whereas ionic compounds tend to have many ions stuck in large chunks, which is definitely going to affect their physical properties. This example here is showing sodium chloride, also known as table salt. So let's start by talking about covalent or molecular bonding. Covalent bonding is what happens generally between 2 or more non-metal atoms. So you guys may remember when we were talking about the periodic trends at the end of the last lecture right before the exam. What we said is that the elements that are very high at the top right of the periodic table, the nonmetals essentially, hold on to their electrons very strongly. They have a very strong pull on their electrons. And that's essentially what makes nonmetal atoms. Whereas on the lower left here, we're on the more metallic side, the metal side is over here. The more down and to the left we go, the weaker the pull on the electrons. And that weak pull is essentially what makes metal atoms. That is why metals can conduct electricity. It's because electricity is electrons that are moving, and since metal atoms don't hold on to their electrons very tightly, the electrons can move around and conduct electricity in the metals. So because the nonmetals up here at the top right of the periodic table hold on to their electrons so tightly, what it means is that when one nonmetal atom wants to bond with another one, neither atom is going to be able to pull the electron away from the other, because both nonmetal atoms will pull very strongly on their own electrons. So the result is that the electrons, when a bond is made, electrons will be shared between two atoms. Let's take a look at what that looks like in a picture. So let's say we have a hydrogen atom here, and it encounters a fluorine atom. Note that the electrons here, these are negative in electrical charge, right? And inside the middle of the atom here, there's going to be a nucleus, which is positive. And so there's an attraction between the negative electrons, represented by this dot here, and the positive nucleus, where the protons are. And the same is true for the fluorine. In the middle of the fluorine here, there'll be a positive charge, and there'll be an attraction to these negative electrons, and it's pulling on them quite hard. Well, what can happen is if these two atoms get close to each other, so as they start to get closer and closer, the hydrogen's moving this way, the fluorine's moving this way, then this electron on the hydrogen can be attracted to the nucleus in the fluorine. And vice versa, these electrons here can be attracted to the nucleus in the hydrogen. And the result is that they will share these two electrons. And so again, the nuclei in the middle of each atom is positive. And these electrons here are negative. So these electrons serve as a kind of glue which holds the positive nuclei together. And that glue is called a chemical bond. In this case, it's called a covalent bond because it happened between two nonmetal atoms, and they are sharing their electrons in order to make this chemical bond. And at that point, the atoms are stuck together. So we've talked about atoms being stuck together before. Now we're going into the reasons why they stick together. It's the electrons essentially that help the atoms stick together by attracting to the nuclei in both of the atoms that are bonding. In ionic bonding, now ionic bonding is going to happen between metal and non-metal atoms, and this is because, again, remember the periodic trend. If we go back to the periodic table, metals, which are closer to the bottom right of the periodic table over here, they have a weaker grip on their electrons. So if a metal atom comes close to a non-metal atom, and the non-metal atoms have very strong pulls on electrons, the non-metal atom will want to pull the electron away from the metal atom completely. And the metal atom won't put up much of a fight because the metal atoms don't pull on their electrons very strongly. So when a metal atom and a non-metal atom encounter one another, the metal atom will give all of its valence electrons to the non-metal atom. And the non-metal will then accept the electrons. And there's going to be a key way in which this happens. And it's going to happen so that each atom has a full shell of electrons, which for most atoms is going to be 8 valence electrons. And so there's going to be a special stability to having 8 valence electrons. And all atoms are, when they're bonding, they're essentially trying to get to this 8 valence electrons. So looking back at the covalent bond here, we can see that the fluorine, if it has both these electrons, it will have 8 electrons represented by this 8 dots. The hydrogen has 2 electrons, and it's because the hydrogen is special. You may remember hydrogen is in the first shell, and the first shell fills with only 2 electrons, unlike the second shell, which needs 8, and the third shell, which also needs 8. And so what we're going to see is that hydrogen will be satisfied. It will stop bonding once it has 2 electrons, but every other atom will want to get 8 valence electrons. So here is an ionic bond being formed between a lithium atom and a fluorine atom. And so we've got a lithium atom. So lithium is the third element in the periodic table. It has 3 protons and it has 3 electrons. And those first 2 electrons go in the first shell. It can only fit 2 electrons. That third electron goes in the second shell, and that is its 1 valence electron. So remember from before where we said the group number is the number of valence electrons? Lithium is in group number 1. It has 1 valence electron. And it's in row 2, so that valence electron is in the second shell right here. Now the fluorine atom, it is element 9, fluorine. It has 9 protons and 9 electrons. 2 of those go in the first shell until it's full, and then the other 7 go in the second shell. Some of those in s orbitals, some of those in p orbitals. But what matters is that there are 7 valence electrons in the second shell. By the way, fluorine is in group 7a right here, and so it has 7 valence electrons. Now, the goal for all of these atoms, and what they don't have goals, they're just atoms, but what ends up often happening is that the atoms will bond in such a way so that they will both get full shells. The way the metal atoms do this is by giving away their relatively few valence electrons that they are not holding on to very tightly. And those electrons pass over and pass to the nonmetal atom, which grabs them. Fluorine, remember, is the biggest, strongest electron puller all the way at the top right here, pulls electrons harder than any atom. So it's just going to yoink this electron and pull it towards itself. And when it does, it will have a full 8 valence electrons in its outer shell. And the lithium atom will have 1 less electron, but it will have a full shell underneath. And so the metal atoms get a full shell by losing their outside electrons, their valence electrons, and exposing a full shell underneath. The nonmetal atoms get a full shell by gaining electrons until they have 8 in their shell. So after this electron has moved, at that point we will no longer have atoms. We will have what are known as ions. In atoms, remember, the number of protons and electrons is the same as one another, so they have no net charge. There's 3 positive charges in the 3 protons here, and 3 negative charges in the electrons. And for the fluorine, there's 9 positive charges in the 9 protons, and 9 negative charges in the 9 negative electrons. But that will change as soon as the fluorine atom steals this additional electron. At that point, lithium will be short 1 electron, and fluorine will have an extra electron. And that's what we're showing here. So now, the lithium atom has now lost its extra electron. It is no longer a lithium atom. It is now a lithium ion with a positive 1 charge. It has a positive 1 charge because it has 1 more proton than it has electrons. And protons are positive and electrons are negative. So since it has 1 more proton than electrons, it has a net positive 1 charge. Mathematically, you can calculate this by, the charge is calculated by doing the protons minus the electrons. So the charge for the lithium here is 3 minus 2, that is positive 1. And we write the charge for ions at the top right part. So that's a special place that we use to write the charge for ions. If it's an atom, nothing's written there because it has no charge. But if it's an ion, you have to indicate the charge. And very often, if it's a positive 1 or negative 1 charge, we'll just write like that. You can write it either way, with the 1 or without there. If it's not 1, if it's 2 or 3, then you have to write the charge. Now, the fluoride, on the other hand, has gained an additional electron. It used to have 9, but now it has 10 electrons. So it has 10 electrons and only 9 protons. So it has 1 more electron than protons. So because electrons are negative, we say that fluoride has a negative 1 charge. And notice that the name is different too. You may think of fluoride as like toothpaste. And this is the ion that is in the toothpaste, fluoride ion. It's no longer fluorine atom. It's called fluoride ion. And it has a negative 1 charge. And you can also indicate this as F minus without the 1. If there's a 1, then it does not have to be written. And again, mathematically speaking, the charge here would be 9 protons minus 10 electrons, which would be negative 1. So that's the way you, whoops, I put it behind my back here. This equals negative 1. So yeah. And so the charge on the fluoride ion there is negative 1. So once that has happened, once the lithium atom is no longer a lithium atom and it's a lithium ion, this has happened because it has lost its valence electrons. And a way that we can represent valence electrons is with dots. So lithium started with 1 valence electron, it no longer has it, and now it's a lithium plus 1 ion. the fluorine atom gained 1 extra electron, so it could have a full 8 now, and now it has 8. And because it has gained an extra electron, it now has a -1 charge because it has 1 more electrons than neutron. How many protons, neutrons, and electrons are in the lithium fluoride ions? Well, to know how many neutrons, we need to know a mass number, which wasn't given to us. But we did see how many protons and electrons, right? The lithium ion now has 3 protons, only 2 electrons. The fluoride ion has 9 protons and 10 electrons. Remember, in ions, the number of protons and electrons is different. In atoms, the number of protons and electrons is the same. So in the last exam, I had you calculate the number of protons, neutrons, and electrons in atoms. Now, for the next exam, I want you to be able to do this not only for atoms, but also for ions. So ions are different from atoms because in ions, the number of electrons is different from the number of protons. Okay, so ions that have more protons than electrons have a positive charge because protons are positive. Ions with more electrons than protons have a negative charge because electrons are negative. For an atom, the number of electrons equals the number of protons. That's what makes it an atom. But for an ion, the number of electrons is going to be the protons minus the charge of the ion. So we had that on the last slide. We saw that the charge was the number of protons minus the number of electrons here. So if we rearrange this algebraically, we can add the number of electrons to both sides. That will cancel this. And we can subtract the charge. We'll subtract the charge here. And so this charge cancels on this side. And we get that the number of electrons equals the number of protons minus the charge. So that is a way that if you have the atom, you'll know, or the ion, you'll know how many protons, and you'll also be given the charge, so you can figure out the number of electrons. So for example, how many protons, neutrons, and electrons are there in strontium 2+ that has a mass number of 88? So first of all, we have to go to the periodic table and look for strontium. So strontium is right here. It's element 38, so that means in the strontium there are 38 protons. Remember, the symbol always matches with the atomic number, the number of protons here. So we can write the number of protons in. It's usually written here if it's written at all. It was what? 38. So 38 protons, okay? So since it's strontium, we know that it has 38 protons. The protons are equal to the atomic number. To find the number of neutrons, so the neutrons here are going to be the mass number minus the number of protons. That's the same as from before. So that's going to be 88 minus 38. That is 50. So we have 50 neutrons. Finally, the number of electrons. So technically, to get the number of electrons, you can apply this formula. So the number of the electrons here will be the number of protons, 38, right, minus the charge, so minus a +2, and so that will give us 36 electrons, okay? The way I like to think of it, though, so I don't have to be memorizing a formula like this. You don't want to memorize. Just think about what +2 means. You know it has 38 protons, right? And it's a +2, which means it has 2 more protons than it has electrons, because protons are positive. So it must have 2 less electrons than the 38 protons. So it has 36 electrons. And that's right here. So 38 protons, 36 electrons. So that's the way I like to think of it. Instead of applying this very specific formula, I just remember protons are positive. So if it's got a 2 positive charge, that means it must have 2 more protons than electrons. Since it has 38 protons, it has 36 electrons. 36 electrons. And so that's how you figure out the number of protons, neutrons, and electrons in an ion. The only difference is that in an ion, the number of electrons is not the same as the number of protons. It's the number of protons minus the charge of the ion. So, we started to introduce the concept of a molecule. So we said that molecules happen when non-metal atoms bond to one another. So it's almost always non-metal atoms that are involved in this. And this can happen either for elements or for compounds. So elements can come in molecular or atomic forms. For example, gold in most metals is just a pile of gold atoms all stuck together. Okay, and they undergo their own special type of bonding metals called metallic bonding. We'll talk about that just a little bit. And nitrogen, for example, is an element that is molecular. Most of the air you're breathing is nitrogen. It's about 79% nitrogen. It has 2 nitrogen atoms stuck together in a covalent bond. We know it's a covalent bond because covalent bonds happen between non-metal atoms. Ionic bonds happen between metal and non-metal atoms. Compounds, these can come in molecular or ionic forms. Okay, so covalent compounds are the ones formed generally from only non-metal atoms. So an example again would be water, and often when covalent, when non-metal atoms bond, they bond to make molecules. So covalent compounds and molecular compounds are words that are kind of interchangeable because generally when covalent bonds are formed, they result in the formation of molecules, which are a certain number, distinct number of atoms that are bonded together in individual units. So with water, it's 1 oxygen atom bonded to 2 hydrogen atoms. You may be wondering why this funny shape? Why not bonded straight across? It's a very good question, which we're going to get to before the next exam. But covalent compounds are often found as a collection of molecules. And so these molecules will have attractions between one another as well, which we'll call intermolecular forces. Now for ionic compounds, so ionic compounds such as table salt are made from metal and non-metal atoms when they bond. Okay, so for example, sodium chloride, which is table salt, has positive sodium ions attracted to negative chloride ions, and these attractions are very, very strong. And so you can see that this attraction extends through a broad lattice. This is just a small, tiny look at the ions. This will continue on and on and on. And so all these ions are stuck together with fully positive and fully negative charges. We're going to call this attraction between positive and negative electrostatic attraction. That's going to be the name of it. And this electrostatic attraction is quite strong. And so what you find is that these ionic compounds do not have individual molecules. Okay, they come in this big block that you see here. Okay, they do not have individual molecules. They come all stuck together, and the result is that ionic compounds tend to be solids at room temperature because all their atoms are stuck, or all their ions are stuck together so hard they can't really move. They're stuck in place, and that's what makes a solid. Whereas molecular compounds have molecules that have strong bonds within their molecules, but not strong attractions between the molecules. So they tend to be liquids or gases more often than ionic compounds are at room temperature. So let's talk a little bit about the strength of the bonds, the attractions. So the attractions between ions are very, very strong. It's an attraction between positive and negative charges. We call that attraction between positive and negative electrical charges, we call that electrostatic attraction. And really, describing all of chemistry and chemical reactions, it has everything to do with these electrostatic attractions, attractions between positive nuclei and negative electrons. So in ionic bonding, we have attractions between cations and anions. Cation is a fancy name for positive ions. I remember that because the T looks like a positive. And anion is the fancy name for a negative ion. I remember that because N looks like N is the first letter in negative. And then this energy tells you how much energy it would take to break apart these ions from one another in a unit called kilojoules per mole. We haven't talked about moles, but you know about joules. It's a type of energy. And so these ions have very, very strong attractions to one another. And for that reason, ionic compounds, their ions are really stuck together and they tend to be solids. Covalent bonds are not as strong. This is an example of a strong bond between hydrogen and hydrogen. Again, this is because there's no fully positive or fully negative ions. There's just a sharing of electrons. So right in the middle here, you see these are the negative electrons, and these are the nuclei. And so the electrons are negative. They're in between the two nuclei, and they serve as a kind of glue to hold the nuclei together. And so the bonds within the molecule is very strong. But what we'll see later is that the attraction between molecules is not nearly as strong. Then for metals, they undergo their own type of bonding, which has to do with the fact that they have nuclei and they have very mobile electrons that can move around. That's why metals conduct electricity, because electricity is just the electrons moving around in the metal. And these tend to have a very wide range of bonding strengths. Also, they tend to be bendable because they don't have any direction to their bonding. Like here, the direction is right between here. Here, the direction is between these ions. Here, the metal atoms are just kind of all on top of each other, and the electrons can move around between them. So that's why metals, you can like bang on them and squish them and bend them. Whereas with like a block of salt, for example, sodium chloride, that's ionic, you could not do the same thing. So chemical bonds between atoms are much stronger than intermolecular forces. So that means attractions between molecules. And so for that reason, ionic compounds with just bunches of ions all stuck together are going to be solid at room temperature. And we're going to see things like molecular compounds, like, and remember, covalent and molecular are kind of interchangeable here. We're going to see that those tend to be liquids and gases, like water is a liquid, for example. Not always, but the bonding is very, very strong in ionic compounds. And the bonding between atoms is strong in molecular compounds, but they have individual molecules, so the attraction between the molecules isn't so strong. Just to go back a few slides and show you the pictures here, to the beginning here, again, you can see the water here has individual molecules. So within the molecule, they have pretty strong covalent bonds between the atoms, but the attractions between the molecules, or the intermolecular forces, are quite weak. And so that is why water is a liquid here. Whereas with salt or sodium chloride, all these ions are stuck together really hard, because one is positive, one is negative. They stick to each other really hard. And so you end up with chunks like this that are solids. Okay, so in terms of naming, we're going to start off by naming covalent compounds. So they talk about this in section 3.2 of your textbook. And the covalent compounds, we're going to talk about those first because those are the simplest. We're going to focus right now only on binary covalent compounds. Binary indicating that we have two types of elements in there. Only two, not more. So like two, binary. If there's more, it can get quite complicated. We'll talk about that kind of naming a little later, or near the end of the class. So we're going to talk about what order we write the elements in for binary covalent compounds. For covalent compounds, we're going to use prefixes, and very important is this is only for covalent compounds. We're going to use prefixes, okay? Only for covalent compounds, because we're going to see that for ionic compounds, we don't need prefixes and we don't write them. And finally, for all these binary covalents, they're going to have an "ide" ending to them. First of all, I'm going to introduce you to a concept called electronegativity, and we're going to talk more about this later, but it's in these numbers here, and you can put these in your notes. I'll remind you later when this is really important to have this in your notes. But essentially, this electronegativity is another property indicating the pull that an atom has on electrons. specifically when they're involved in a covalent bond. And again, we said at the top right of the periodic table where fluorine and oxygen are, those have the strongest pulls on the electrons. And you can see that by their higher electronegativity number here. And this gets smaller and smaller as you go down and to the left on the periodic table. Basically, if an element is on the left and down on the periodic table, you'll tend to write it first when you're writing the names and the formulas for covalent compounds. And if it's to the top and the right, you'll tend to write the symbol or the name of it second. So the element with the lowest electronegativity value will be written first. You don't have to memorize these numbers. Just know if it's more down and to the left, this will be lower. And so you'll put these first, and then you'll put other elements second. This isn't always the case, but it very often is, most of the time. So for example, if we're talking about carbon monoxide, which has formula CO, one carbon atom, one oxygen atom, we write the C before the O, and we write CO, not OC, because carbon is more to the left on the periodic table than oxygen, and it has a lower electronegativity. And then also, only in covalent compounds, we're going to use prefixes to indicate how many of each atom that we have, only in covalent compounds, never in ionic. So we see this P2O5. We can recognize that this is a covalent compound, not an ionic compound, because phosphorus and oxygen are both nonmetal atoms. So this must be a covalent compound because it only involves nonmetal atoms. We're going to use these prefixes here, which you should memorize. So you should memorize these to indicate how many of each atom we have. Mono is for 1, di is for 2, tri is for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, deca for 10. From here to here, these follow the same as polygons. These are like polygons. Like you've probably heard of the Pentagon, you know, which is 5-sided building where the military is, or the octagon where the MMA fighters fight. These ones are a little bit different, the first 4 though. So here with this one, the way we're going to write this is we're going to say di, and then we're going to write the name of the first element, phosphorus. And then we're going to write penta, because there's 5. So di because there were 2 phosphorus, and then penta because there's 5. So we're going to say penta oxide, or some people say pentoxide. That's okay too. Diphosphorus pentaoxide. And that's how we'll write the name for covalent compounds. We always end with "ide" for the binary covalent compound. So we don't say diphosphorus pentaoxygen, we end with "ide" on the second one. So there's a few exceptions to this. So when the first prefix is mono, we don't write it. So when we have CO, we say carbon monoxide. We don't say monocarbon. If mono is at the very beginning, we don't write it. Or silicon tetrafluoride. We don't say monosilicon, okay? Because we don't put mono at the very beginning. And then you might have noticed an exception here. Like this, we said monoxide, or here N2O, we say dinitrogen monoxide. We don't say monooxide. Instead of having the 2 O's, we just say monoxide. I think because people just like the way it sounded better. And so those are the 2 exceptions. Number 1, never put mono at the very beginning on a covalent compound. And when you have monooxide, you don't say monooxide, you just say monoxide. So remember that in these compounds, they're binary. The ones we're doing, they only have two types of atoms in them. So the second one is always going to end with "ide," and this is what it looks like for each of the common non-metal elements. Hydride for hydrogen, carbide, nitride, phosphide, oxide, sulfide, fluoride, chloride, bromide, so forth. They end with "ide" if they're at the end. "Ide" goes at the very end. So name to formula, pretty easy. Sulfur dichloride. Remember, we never have a mono at the beginning, so it's just S. And then dichloride means two chlorines, SCl2. That. Dinitrogen tetraoxide. So di is the prefix for 2, and tetra is the prefix for 4. So we have oxygen, 4 of them. Notice we always end with "ide" on the name, right? "Ide." But we don't put "ide" in the middle. This is actually a component of smog. Carbon tetrabromide. So remember, if there's no mono at the beginning, that means 1. So we have 1 carbon. And then bromide is indicating bromine. And we have 4 of them. That's what the tetra means here. CBr4. So if you're given the name and asked the formula, that's how you do it. What about if you are given the formula and asked for the name? Well, that's what we did here, right? CO, carbon monoxide, SiF4, silicon tetrafluoride, and so on. And so that's how you name binary covalent compounds. Relatively easy. Remember, you use the prefixes for these. In the next lecture, we're going to talk about how to name ionic compounds, and what's going to be really important there is that you do not use these prefixes for those. Only for covalent compounds, use the dis and the tris and the tetras. For ionic compounds, we're not going to use those, and the naming and the writing of the formulas is going to be quite a bit more involved. And so I'll see you on the next lecture.